quick summary in a nutshell. Go ahead. So we started with electromagnetic spectrum, and
Yeah,
then
we had like X-rays, and then ultraviolet.
X-rays, ultraviolet. So one thing is you have to have it
White
memorized.
light, and then
X-rays, ultraviolet, visible, and then infrared.
infrared, microwaves,
Microwaves,
radio.
radio waves, TV. And just one was missing. One before, yeah, gamma. Good. All right, and then what? Then what?
We also talked about orbitals.
Yeah, but before we got to the orbitals, you know, what did we talk about?
About photons.
We also talked about photons, but this is part of what you should be doing at home as homework. You know, as homework is you should try to be summarizing, you know, all the content, the lecture. If somebody asks you what are you covering, you should be able to tell them. If not, then make sure you ask questions. If you don't, you know, understand what's going on, or you know it doesn't make sense, then make sure to ask some questions and get it clarified or read through. There are different sites you can go to, including Khan. But basically, we talked about electromagnetic radiation. We talked about spectroscopy. Then we talked about what was expected and what was unexpected, the unusual line spectra that led to the theory, which is quantum theory. Now, quantum theory is our current modern day theory of matter. Let me see if this is working now. And our book does talk about it, but it doesn't go into that much depth. So we have this in the supplement here, quantum numbers and electronic structure. And so let's just take a look at the supplement here to get the questions. This is where you're going to go, quantum 1 through 5. So let's go to quantum. Where do quantum numbers come from? Well, this is stuff you don't want to cram like the night before. This is stuff that you want to have a review or be able to review a number of times before the test. And so where do the quantum numbers come from? They are the energy levels. That's what the quantum numbers are, but where do they come from? See, so...
The electrons. The first electron.
Well, the quantum numbers describe something, and it describe something, and they come from somewhere. And yeah, they come from somewhere. And so you want to figure out where they come from and the other stuff regarding quantum numbers. You can just read about it. Just read about it here. That's what they are, but where did they come from? That's the question. That would be a typical multiple choice style question. But you still have time until the next test. You want to review it. Quantized energy levels, yeah. And so all that stuff is correct, but I think I'm asking too early right now because it sounds like people haven't reviewed yet. So we'll ask again as it gets closer to the test. What we'll do is we're going to take a look at the quantum numbers here. And so we did all this stuff, right? And so I recommend reading through this here, and then we generated the quantum numbers here. But I was going to go through these questions, but maybe it's too early. You haven't had a chance to read through it, seems like, or at least review your notes. And so take a look at quantum 1 through 11 in your lab supplement, and then that'll be helpful. Thanks. So we're going to continue. I'm going to finish up chapter 11, and then we're going to move on to chapter 12. And then when you have a chance to take a look at quantum, then we'll come back to it. But I think it's not going to be very effective use of time. I'll get all in there. So basically, I said that quantum mechanics is the current modern day theory of chemistry. And so, in fact, the periodic table is developed in Mendeley's time before quantum mechanics. But you can see that the periodic table is just based on orbitals and how the electrons fill. So for example, hydrogen has a 1s orbital with 1 electron in it. And then helium has a 1s orbital with 2 electrons in it. And so we built it up through here. And then we talked about certain things that you have to have memorized. But this is, this is probably, I'll talk about chromium and copper later. But what you want to do is you want to get it based. Last time I left off talking about the half fill, or the half, how you slice a cake in half. You recall that? And there's a special symmetry that's allowed. And those are going to be certain exceptions within how this fills. But you can see on the sublevels, how many p orbitals are there? Let's say 2p. How many p orbitals are there? O equals 1. With 3 orbitals. Each orbital holds 2 electrons. So this would be, 2, 4, 6 electrons. That would completely fill the p sublevel. Fill this sublevel or subshell. The s holds 2 electrons. So each element is 1 extra electron here. The d's hold a total of 10 electrons. The f holds a total of 14 electrons. So there are 14 elements that go across, each one adding an additional electron. And so what we need to do is this. So chromium and copper, I'll talk about that again later. So I'm going to skip it for now. Chromium and copper. Maybe it's if you're having trouble with this, the other stuff, it's going to be a little bit confusing. So we'll take a look at just the standard chromium and copper later. So I'll come back to that. What we're going to do right now is we'll just pick an element like carbon. There are different ways we can show the structure, electronic structure. One is this, and I'm going to use the abbreviations here rather than the 100. I'll just call it the 1s, 2s, 2p. What comes after the 2p? 3s. You have to memorize this table. So just start memorizing this table. Worry about understanding it later. Now, the first part of learning anything, especially things that are difficult to learn and difficult to understand, is just to memorize first, and then with time, it'll start making more and more sense. When you get into like advanced classes, like graduate level or upper division, or go to conferences, a lot of the stuff just doesn't make sense. It takes a lot. If it was easy, if you could just sit there and just absorb it easily, then you'd have a PhD in no time, which would be great. But as you get more and more advanced, the stuff it just doesn't And so just be aware of that a lot of people find this stuff difficult and it never clicks for them. And so you need time to let it absorb. It doesn't, don't expect it to be easy because it's not so easy. And so what we do is we just try to memorize certain things that aren't that difficult to memorize. So for example, 1s, 2s, 2p, 3s, 3p, and then what comes next energetically?
3D but 4S.
Yeah, good. Yeah, 3D but 4s. 4s comes because that's actually the 3D gets put up in the what shell? What shell did we say the 3D gets put up in? Fourth shell, good. It's 3D. And then the 4P rounds out. What about the 4D? Does the 4D go in the fourth shell?
No.
No. And so you need to memorize the first 4 shells. The first 4 shells are this. The first shell is this first row. The second shell is the second row. Third shell, fourth shell. So we're going to memorize, figure out the first 4 rows of the periodic table, how those elements fill, except for copper and chromium. We'll talk about that later because those are a bit more complicated. And so, for example, carbon has all the other 6 total electrons, so we fill it using the rules that we talked about earlier, and so we end up with this. And so carbon, we only really need the first 2 shells, but you need to know this to the first 4 shells, at least the first, and also the names of the elements you need to know here for the first 4. Now this is big. What is this diagram called? If somebody asks you, what is that diagram called, what would you tell them it's called? Energy level diagram, good. And so if somebody asks you for an energy level diagram, you do this. Or more specifically, orbital energy level diagram, or atomic orbital energy level diagram. Because these energy level diagrams, we have lots of different ones. So we can go short and just call it an energy level diagram, or we can be more descriptive and call it an orbital energy level diagram, or we could be even more descriptive, call it an atomic, because there's something called a molecular orbital energy level diagram, which you saw a few of them because I was scrolling through some of those. Those are quite a bit more involved, so I'm not going to talk about those at all. I'm going to skip them. In organic chemistry, you deal with molecular orbital energy level diagrams quite a lot. And so we do this to the first 4 shells, memorize it. So that's not terrible. But, drawing it out, you have to draw it out. This whole thing you got to memorize, including the relative energies. The next thing you need to do is this. We need other ways of showing this. So we have something called an orbital box diagram. An orbital box diagram has an advantage of taking less space, but it has a disadvantage of not giving you as much information. You lose information when you go to orbital box. So this is kind of like the molecular formula or structure, molecular versus empirical, or something like that. We lose a little bit of information. The orbital box diagram, what information do we lose? And so if I were to do this orbital box, I'm going to just do the first 2 shells. And then for carbon, it's going to look like this. And so what information did we lose? Yeah, the relative energy level. So we see energies increasing this way, but we don't see the gaps, and so that's missing that information. But what's even worse is something called electron configuration. Electron configuration, well, it's worse in the sense that we lose a lot more information, but it's good in the sense that it's the most compact way of representing this. The most compact way of representing this is to say a 1s orbital, and we do this superscript 2. So this is not read 1s squared, it's read 1s2. And then this one would be a 2s2, and this would be a 2p2. This is telling us the total number of electrons in that subshell, and we'll just represent that subshell as this. Something that can also be done is this, like a 1s2, 2s2, 2px1, 2py1. 2pz would be 0, there'd be no electrons there, so we would bother with that. And then there's one more way of doing this. One more way of doing this is we do HE for the first shell. Because you know, when we first fill the first shell, that's filling the first row of the periodic table, which is helium. And then the second row of the periodic table, so HE is up to here, and then all the way up to here we have argon, which is filling the second shell. And then filling the third shell, we have, oh, not argon, sorry, neon. And then filling the this first, second, third shell is going to be argon. And then filling the fourth shell completely will be krypton. And so these are called Nobel gas core abbreviations. So what we could do is we could use the helium core and then just say 2s2, 2px, or we just don't do the x, y, z that much. We just do 2p squared. And so this is an alternate way of showing this. These are electron configurations. So you have to, you know, if I ask for an energy level diagram and you write an orbital box diagram, you know, you're giving me the wrong thing. Some people would give 0 points for that, you know, because they think, oh, you don't know what you're talking about, so you deserve 0 points. You know, I'd give partial credit, but I'm going to deduct because you don't know what you're talking about. You didn't memorize the names for these things, which you have to have memorized. Right?
For the orbital energy level one, do you always start at the bottom and then go up?
Yes.
Okay.
Always start. When I do an orbital energy level diagram, I'll do the whole thing. Now, the book doesn't always do that because there's not enough space and it's wasting paper. But I always do. Otherwise, it's easy to get mixed up when you do that. And you got to be consistent. Some books will only do what they call the outer shell. And so the outer shell is the shell, the highest shell with electrons in it. So this would be considered the outer shell. The outer shell has another name, outer shell, and that's called the valence shell. And then we have the inner shells, or inner shell in this case. This is only one, but we could have more than one. The inner shells, these are called the core electron, or the core shell. And so in this case, we have the helium core, and the valence shell would be this, 2s2, 2p2. Now it turns out the cores are unreactive, chemically, unreactive. The valence, this is where all the reactivity is. So these are reactive, potentially reactive. Depends on what you react with. And so something can try to strip the electrons off the carbon there. You're going to be able to strip the outer ones, but the inner ones are going to be hard to strip off. Or carbon can strip electrons off something else. Carbon strips electrons off something else. You know, what are the charges on carbon? What is the charge range? Yeah, 4, -4. So if something comes in and strips all the electrons off, then this carbon's going to lose 4. Why doesn't it lose 6? Because it has 6 electrons. Why isn't +6 okay for carbon? Well, there are 2 ways of answering it. One way of answering it is, oh, +6, that exceeds the maximum, right? And then somebody might ask you, well, where did you get the maximum? You know, why did you come up with that number? +6. Well, here's where that number came from. The number came from +4 is stripping off all 4 of the outer shell electrons of the valence shell electrons of the valence electrons. Now the core are very difficult to strip off. They're very tightly held. And so it is possible to strip them off, but you need something very powerful, and that something very powerful would be very unusual, very rare in that case. And so here, the other option for carbon is it could gain how many? If it gains 4 electrons, like say here, if carbon gains 1, actually we fill over here first, 1, 2, 3, 4, we complete the second shell. If it gains 5 electrons, then that 5th electron would have to go into the into the next shell that's unfavorable. And so this is where those numbers come from, the maximum and the minimum, what we call a oxidation state. And so this is why this is a more fundamental, because earlier I just said, okay, +4 is the max, so if you got +6 it doesn't work. But now we have a better description of what's happening, and that better description is what we call, theory. A theory should be a better description of what's happening. Underlying what's happening. All right, so the earlier question was, in an energy level diagram we show this, but when we're doing electron configurations, we typically show the 4. Right? And so you can see here, 1s, actually 2s2, they really didn't show it here. Because I guess it's not so difficult. So they didn't show the helium. They could have done helium in square brackets and did this. So what we did for carbon over here is 1s2 is helium. So we give us a helium, 2s2, 2p2. But take a look at what they did for silicon. Silicon, what they did was they went to neon with 10 electrons and just added them from there. And so for silicon, it'd be neon 3s2, 3p2. For these, it would be argon. And so that's going to save you a lot of writing, by using these Nobel gas abbreviations here. And so, for example, vanadium is argon 4s2, 3d3. Chromium you'd expect to be argon 4s2, 3d4, but it's not. Chromium's an exception. The same with copper. Chromium and copper is kind of weird when you look at it, the pattern. But other than that, it's fine. What else do we see? What else we see is that the family members all have the same outer shell electron configuration. So hydrogen, 1s2, lithium, 1s1, 2s1, sodium, 3s1, potassium, 4s1. The cores are going to be different. This is helium. Oh, actually, there's no core here. This is helium core, neon core, argon core. Group 2, they all have the S2, the NS2, we call it. So this is the NS1, N just shifts depending on which row. This is the NS2. And so all members of the family have the same valence shell electron configuration. Okay. Except here, this is a little weird because this says 2s2, 2p2, that's carbon. And so there are 4 electrons in the valence shell. Over here, silicon, 3s2, 3p2, it's 4 electrons. But when we get to germanium, take a look at germanium, 4s2, 3d10, 4p2. So all of a sudden we jump from 4 valence electrons here to 2, 10 is 12, plus 2 is 14. Is that right? Germanium have 14 valence electrons. And the thing is this, even though these Ds are in the 4th shell, it turns out, we didn't get into the quantum mechanics of this that much. But it turns out when the N changes, what happens? 1s orbital, about this big. What happens when you go to 2s orbital? It gets bigger, 2s orbital. 3s orbital, even bigger. And so the situation here is when we're looking at the 4, the 4s are big. These are huge orbitals. But a 3 is a lot smaller. If it's a lot smaller, it's going to be closer to the nucleus. And so even though these are in the 4th shell, but considered inner shell. And so it's in the 4th shell for filling, but it's in the 3rd shell for reactivity. That is, if you're an oxidizer, imagine you're an oxidizer, you're coming to take electrons. What electrons are going to be the easiest to remove? The ones that are furthest away from the nucleus, or the ones that are closer to the nucleus? The furthest away. And so if you're an oxidizer, you're not going to pay any attention to these 3D electrons. You're going to be paying attention to the 4s and the 4p. And so what's the maximum positive charge of germanium? +4. Just like silicon, just like carbon, same family. It's because the 3D, there are two reasons. The 3D are considered inner, and this 3D is filled. When you have a filled subshell, there's additional stability associated with that, so this is 3D10. So these 3D10 are considered core unreactive, just the 4s2 and the 4p2. And so it is the same valence shell electron configuration, even though the valence shell looks different here. And so that's what we see here. We can use a periodic table to write more complex electron configuration. You see this? Writing electron configuration exception. Interruptions appear among 3D electrons like chromium and copper. Well, let me talk about that briefly now, so we hit that point. If we look at chromium, how many electrons does chromium have in total? 24 electrons. So that's our starting point. We have 24 electrons. And so we'll generate the orbital energy level diagram for chromium. Starting at the very bottom, 1s, 2s. What's after 2s?
3s.
Not 3. 2p.
3s.
3s. 3p.
4s.
4s.
4p.
No. 3d. 3d are going to be higher in energy.
So we just skip 4p.
No, we still do 4p. 4p is right above. And so this shell's funny. The 4s and the 4p would be considered the valence, and the 3d would be considered inner shell, even though it's in the same shell, you think. But it's just funny the way it works. And so we got 24 electrons, so we just fill it. An arrow up, that's 1. Arrow down, that's 2. 3, 4, 5. How do I fill this? These are energetically degenerate. What rule do I use to fill those? Hund's rule, yeah. We can use Hund's rule. 1, 2, 3. So 2, 4, 5, 6, 7, 8, 9, 10. So that takes me to 10 electrons here. 11, 12, 13, 14, 15, 16, 17, 18. 18 electrons here. So 2 electrons for helium, and then I'll go up to here. 10 electrons total for neon. 18 electrons total for argon. 18 total. So 18, 19, 20, 21, 22, 23, 24. There I am at 24 electrons. 24 electrons. Now what happens is this. There's some stability. So extra stability for 1/2 filled and filled D subshells. So what happens is this is 1 electron shy of being half filled. If it's 1 electron shy of being half filled, then what happens for chromium is this. You know, there's not a huge energy difference. So one of these electrons can get promoted to here and half fill it. And so what this is going to look like is something like this instead. look like is this. So I'll abbreviate it up to here is argon. Then we'll go to 4s. It's going to be 4s1, and then we jump up to the 3d. The 4p are empty. There's nothing there. This is 3d. And it has to do with the symmetry that's allowed. So even though the 4p are empty, I'm going to still write them up here. And then they're higher energy orbitals, which I'm not going to bother writing, but I just want to complete this shell. And so as far as electron configuration goes, it's going to look like this. Argon, 4s1, 3d, 5. What we expected was argon 4s2, 3d, 4. This is observed. What was expected was argon 4s2, 3d, 4. This only works for one electron. So for example, vanadium, it doesn't work. Vanadium is argon 4s2, 3d, 3. So why don't I just take both those electrons and bring them up here? And so I can make argon 4s0, 3d, 5. But that means promoting 2 electrons. Promoting 2 electrons is too much. Promoting 1 electron is acceptable. Promoting 2 electrons is unacceptable. So that's what we have. Otherwise, everything else follows the pattern. So let's just take a look up to chromium right now. So when we get at scandium, we're at argon 4s2, 3d1. Titanium, argon 4s2, 3d2. Vanadium, 4s2, 3d3. It's 2 electrons shy from that will. Chromium, it should be 4s2, 3d4, but 1 electron gets promoted, it goes 4s1, 3d5. Manganese, now we'll just fill in. Manganese naturally is 4s2, 3d5, so manganese naturally has a half fill. Iron, we have no choice. We're going to go 6. So it's 4s2, 3d6. Cobalt, 4s2, 3d7. Nickel, 4s2, 3d8. And then when we get to copper, copper should be what?
4s2, 3d9.
Yeah. Copper should be 4s2, 3d9. Well, 3d9, that's only 1 electron shy from filled. And so copper does exactly the same thing. What happens with copper is an electron gets promoted from 4s to completely filled 3d.
So do we have to always promote an electron to do that? Do we always have to fill it in? Do we always have to make it half full? Can we not just leave it like 1?
Only for chromium and copper. Chromium and copper, those are the ones you memorize. But manganese already has a half fill. And then zinc already has a fill. So if you look at zinc, zinc's no problem for us to 3d10. Remember, what's the charge on zinc?
2+.
2+. Is it fixed charge or variable charge?
Fixed charge.
It's fixed charge. Zinc is always 2+. And that's because of this. If an oxidizer comes along, it's going to take the 4s2 electrons, but it's not going to touch the 3d because those 3d are considered core and it's filled. When you have partially filled, then it's easier to take. So for example, what are the charges on iron? 2 and 3. So if an oxidizer comes along, it's going to pluck off the outermost, the 4s2, and leave this. But this is 3d6. If it's 3d6, if it loses 1 more electron, it would be 3d5. And therefore, yeah, so +2 and +3. In fact, most of these transition metals have a +2 charge because of losing the 4s electrons here. And then you can lose some of the Ds, depending on how aggressive the oxidizer is. And so this is, again, theory should describe reactivity. Okay, let's do a more difficult one here. And we'll need a periodic table to do that. We're gonna do it based on the periodic table. If you look at, zinc here, it's, you see it's 2. We have Roman numeral 2b and we have Roman numeral 2a. Roman numeral 2a is for group 2. These are pseudo group 2. These are pseudo group 2 because of the electron configuration. Essentially these have 2 valence electrons. The 2 valence electrons would be the 4s here in this case, 4s2. This 3d10 are considered core and it's filled, so it's very stable. So the core electrons are going to be here, argon 3d10. The valence would be 4s2. That's for zinc. Let me say a few more final words about zinc. Whereas copper, this is argon 4s2, 3d10. Now, there's 2 ways of writing electron configuration. This is how they fill. So this is filling order. And then this is the losing order, which is numerical. 3d10, 4s2. So 3d10 and the argon, these are considered core. This is considered valence here. And 4s2. And so if an oxidizer comes along, yes, the 3d10 were higher in energy than the 4s2. The 3d10 were higher in energy than the 4s2. However, the 4s2 are further away from the nucleus than the 3d10. And so those are going to be lost first. And so zinc loses 2 electrons to form the zinc ion. It's going to look like this. So minus 2 electrons. So an oxidizer comes along, and then we're going to end up with Zn2 plus. Zn2 plus is going to be argon 3d10. The 4s2 electrons are gone. What about cadmium? Cadmium does the same thing. The core electrons for cadmium are krypton 4d10. So that's the valence electrons. It's got 2 valence electrons, it's plus 2. This is pseudo group 2b. What about copper? Well, you'd expect the core electrons to be argon 3d10. You'd expect it to be 1 valence electron. So copper plus 1 should be common charge. Well, copper plus 1 is common. That's not the most common. What's the most common charge for copper? Plus 2. So plus 2 screws up my 3d10. So what happened there? Didn't I just tell you 3d10 and 3d5 or d10 and d5 are stable?
So D9 is not that stable.
D9 is not that stable. And so why is it that copper plus 2 is much more common than copper plus 1? It contradicts what I just told you. And the reason it contradicts what I just told you is because of something else. It depends on the structure of the compound or the structure of the ion that copper is. And so it turns out that D9 is stabilized in another way. And so that comes in Chem 1B. So it's too early to talk about. Yeah, it doesn't make sense, but it makes sense once you see what's going on. But we aren't going to see what's going on in this class. However, silver works nicely. What's the charge on silver?
Plus 1.
Plus 1. So silver behaves properly You'd expect krypton 4d10 to be the core, and it would be +1. Now what happens with these guys, like nickel? Nickel is +2,
And 4.
+3, +4. And so nickel is +2 for sure because you lose those 4s. But the +3 is losing one of the d8s. +4 is losing another. You know, there's a certain limit because the more electrons you lose, the more difficult it is to remove the next one. And so if somebody's already lost 3 electrons, it's very hard to take the 4th electron from that species. Because of the charge that are generated. All right, that's a little bit of chemistry. Let's just go back to looking at electron configuration. And so let's say I want the electron configuration for uranium. Yeah. Uranium's element number 92. So what is electron configuration for that? That's 92 electrons, so that's a lot of electrons. Electron configuration in uranium. So 92 electrons. Well, here I don't want to start from 1s because if you start from 1s, it's going to take too long. And so what you do is you work backwards and find the nearest noble gas going backwards. So it's 92. What's the nearest noble gas going backwards? 92. Is it 118 or is it 86?
86.
It's going to be 86, which is radon. And so what we'll do is we're going to do this. We're going to use the Rn, and this takes care of 86 of the 92 electrons. So that's 86 electrons. Where does the 87th electron go? So if that's the 86, we look for number 87 next. Yeah, it's francium. Here, do you see it? This is the 87th electron. This is the 7th row, or 7th shell. And so that means it's 7s1, 2. Take us to radium. 7s2. Okay, that gets us to 88. Now we gotta go to 89. Where's 89? So do you see this? It says 89. Well, you have to go down here. There wasn't enough room to insert this. Otherwise, the periodic table would be very long. And so what we have to do is this next shell would be super long because the next shell would have a lot of electrons in it. And so what we're going to do instead is we're going to insert this row. It should be here, but to make the periodic table more compact, we're going to drop down to here. And so what is this? Well, the 3Ds are way up there. These are the Fs. And the Fs start at 4F, and then this would be 5F. So that's going to be 5F. And then 1, 2, 3, 4. According to this periodic table. Now take a look at the electron configuration there, 5F4. Do you see the electron configuration they have there for uranium? Let's take a look at the electron configuration they have for uranium. I don't know, maybe blow this one up that much. What do they have? They have radon. Okay, they're doing it in the the losing order. The losing order is just numerical order. And so they're going 5, 6, 7. Do you see that? Because 7 are the outermost, so they're going to be the first lost. And then the 6 are going to be the next lost, and then the 5. So we got 7s2, 5f4, but they got 7s2, 6d1, 5f3. Do you have to memorize that? It turns out you don't have to memorize it. You just have to use a better periodic table. So if we use the, and you're gonna get a better periodic table. Here. Let me show you what I mean. There are two styles of periodic table. You have two styles of periodic table. You have the style that's shown. Okay, sorry. I thought all the images they've seemed to have edited, but we don't have them. You have the style that's like this, right? And then you have the style that's like this, but this is kind of hard to see for you guys here, probably. But this is the other style of periodic table. You see the difference here. The difference is, look at what happens. We go 87, 88, and then where's 89? 89's here, and then 90 is here. And so this is two different styles of periodic table. Take a careful look here. You see this? Totally different. Now, this style is much easier to do electron conversion. With this one, we would have done radon, 7s1, 7s2. Then 89 is 6d.
What?
1.
6. 70.
No, because it's offset. The d's are offset. Remember the shells? In the fourth shell, you have the 3d. In the fifth shell, you're going to have the 4d. The d's are offset by 1. Okay, so in this periodic table, we go here, 7s2, 6d1, and then when we go 89, jumps down to 90 here. And so we go 6d1, 5f1, 2, 3. So it depends on the periodic table we use. If we have a periodic table like this, then no problem. We can do the electron configuration. If we have a periodic table like this, then we have to memorize it. And there's debate about which periodic table. It looks like the people who like this periodic table have won the debate because, at least on Google, I can't find the other periodic table on Google. This is very odd because it used to be easy to find.
So how would you number the rows for the F one?
4F and 5F.
4F, 5F?
Yeah. We got this little thing for remembering. Well, just actually, it's easier just to memorize it. It's not that hard to memorize. You can memorize it based on this PowerPoint here. See, the fourth shell is 4s, 3d, 4p. The fourth shell. The seventh shell would be s, f, d, p. Be 7s, 5f, 6d, 7p, etc. So we could get the electron configurations, even for the weird ones like uranium off the periodic table. We don't really have to memorize it, use the right periodic table. Okay, now we want to understand more of the chemistry that's going on. And we talked about the valence electron. It turns out the valence electrons is where the chemistry happens. The core electrons are pretty much untouched. And so what we can see is if we go across the third shell here, we call this the third period. If we go across the third period, it starts off at sodium and ends in argon. And if we're going to just do a total count of the number of valence electrons. So, sodium is the 3s1, magnesium is 3s2, aluminum is 3s2, 3p1. All these are going to have the same core, the argon core. And so when we count the total number of electrons as 1, so we represent that one electron with a dot. The core electrons aren't shown. This is called the Lewis symbol. Magnesium is going to have 2 dots, aluminum is going to have 3 dots, silicon is going to have 4 dots because it has 4 valence electrons total, and it's 2 and 2. So those electrons can be attacked. The maximum positive charge is +4, because this is all 4 of those. Phosphorus, 5 valence electrons, so 5 dots. We can lose all 5 of those, or we can gain 3. If we gain 3, then it completes that shell. Sulfur, chlorine, argon. Argon's filled shell. Filled shell that's 8 electrons, 8 valence electrons. So, the important ones that we're going to do, we're going to do the second period. Second period are going to be important. Here. Starting with lithium. Okay, if I want to draw the Lewis symbol for lithium, how many dots would it have?
One.
Yeah, just 1 dot. So lithium would look like this, 1 dot, anywhere. We divide the space here into 4 regions. Sometimes we'll pair up the dots, sometimes we'll leave them alone. Beryllium, 2. This one will pair up, but it doesn't really matter. Pair it up. Okay, then we go to boron. 3 dots. Okay, for boron, what we usually do is we leave them single, all single. So boron would be like this: 1 here in this region, 1 here, 1 here. So this 4th region will be empty here. After boron comes carbon. Carbon, we have 4 singles in the 4 regions. Then comes what? Nitrogen with 5 valence electrons, 5 dots. Now we're going to pair. And so we'll pair, that is, in this region, and then 3 singles. This. And then oxygen. With oxygen, we're going to write 2 pairs.
Professor, does it matter which ones we pair it with, or
No.
okay?
Right? You could do it in any of the 4 regions. Nobody really cares. And then fluorine.
7.
Yeah, 7. So fluorine's going to consist of 3 pairs like this, and 1 single. And then neon. Neon is 8. 8 electrons will completely fill the s and the p orbitals, so we call this filled. And it's a total of 8 electrons, so we call it a filled octet. 8 electrons. The filled octet, that filled shell is stable chemically and somewhat unreactive. So these are electron configurations. We have to get good at writing out electron configurations. So visually we can see what's happening. Carbon, what are the charges for carbon? +4.
+4, -4.
Yeah, if we lose all 4, then we're stripped down to the core, which would be neon. Or if we gain 4, then what we've done is we just filled
Also
that
neon?
shell.
Would that also be neon or?
Yeah, that would be neon. That would be the same as neon, right? Neon's stable. So fluorine wants, in order to fill the shell, fluorine wants one powerful oxidizer. Oxygen wants 2, nitrogen wants 3, carbon wants 4. Yeah. These ones, boron's not that powerful, so boron needs 1, 2, 3, 4, 5. But boron has a hard time taking 5, so boron's more likely to lose.
Lose 3.
Yeah. Same thing with beryllium. Lose
3.
2 and lithium loses 1. Then we're left with the core. I think, did I make a... Alright, so that's the helium core would be it. The Lewis symbols are important for understanding chemical properties and other stuff. But what we're going to do next is we're going to look at some physical characteristics of the atoms. So these are Lewis symbols. This is tellurium. Tellurium has how many valence electrons does tellurium have?
6.
Yeah, 2, 4, 6. So it'd be like oxygen. 6 valence. What's the difference between tellurium and oxygen? What's one big difference between tellurium and oxygen? Yeah, the core is going to be, tellurium is going to have a much bigger core. Oxygen is a much smaller core, just helium. Tellurium would have one core associated with it. It'd have the krypton core. This is a lot bigger. And so that translates to this. Which one's going to be a bigger atom? Oxygen or? Tellurium is a much bigger atom. Since it's a much bigger atom, much bigger atom, than oxygen. So that's going to change its chemical behavior a little bit. And the chemical behavior, actually, it's just about time for a break. We'll talk about the chemical behavior in just after our break here.